Take a look at this Aviation dispatch printout. It displays a single line of raw text. To the untrained eye, a string of characters like this looks like absolute gibberish. By the end of this video, you will be able to look at this exact string and instantly visualize the weather conditions at an airport, understanding the specific impacts on a flight, just like a professional pilot. Grab a piece of paper and write this string down right now. We are going to decode it actively, step by step, alongside one another. Mastering this decoding process is the essential first step to transition from a passive passenger into someone who thinks operationally about the atmosphere. This diagram shows our full text string. Let's start by isolating the first 3 blocks. This gives us the report's baseline metadata: what it is, where it is, and when it was taken. The first block is METAR. This translates simply as a routine current weather observation report. Next, we have the unique location identifier. The letters DNMM specifically designate Lagos International Airport. The third block holds our timestamp. The first 2 digits, 27, represent the day of the current month, so this observation was taken on the 27th. The remaining digits and the letter Z give us the exact time of the observation. In aviation, 1500Z means 1500 hours in Universally Coordinated Zulu, or UTC, time. Establishing the who, where, and when is a mandatory prerequisite. Before a pilot can trust or apply any of the actual weather data that follows, they must verify they are looking at the correct airport at the correct time. Let's transition to the next 3 blocks of code. Group these together on your notepad as the surface conditions segment. We begin with the wind. The first 3 digits, 240, indicate the direction the wind is blowing from on a standard 360-degree compass. The next part, 08K, is the wind speed, measured in knots, so we have an 8-knot wind. The 8000 block dictates our horizontal visibility. In this international reporting format, the unit is measured in meters. The observer can see horizontally for 8,000 meters, or 8 kilometers. Moving to the -RA block, we decode the precipitation. The minus sign at the front is a specific modifier for intensity. It translates to light. The RA identifies the specific weather phenomenon, which is rain. Combine the terms and we have light rain. Check your notepad. You should now have successfully written the complete surface translation. Wind 240 degrees at 8 knots, 8,000 meters visibility, light rain. Understanding these specific surface variables dictates the immediate physical handling of the aircraft during the critical phases of takeoff and landing. Now we shift our focus from the horizontal plane to the vertical plane by isolating the final 4 blocks of the METAR. The first 2 blocks here are our cloud coverage codes. SCT translates as a scattered layer of clouds, and BKN translates as a broken layer. To read aviation cloud altitudes, you must apply the add 2 zeros rule to the digits. Miscalculating this is dangerous. 012 is not 12 feet. Add 2 zeros and it becomes 1,200 feet. The 025 becomes 2,500 feet. We can now map those translated altitudes onto our vertical scale. The scattered clouds sit at the 1,200-foot mark, and the denser broken clouds are at 2,500 feet. The next block, 26/24, gives us the local temperature and dew point, measured in degrees Celsius. The temperature is 26 degrees and the dew point is 24. Our final block is Q1012. This is the altimeter setting, representing the current sea level atmospheric pressure. Do not panic about the complex mechanics of barometric pressure right now. For today, simply identifying this as the required altimeter calibration setting is your only goal. Mapping this vertical profile is essential for determining the exact altitude a pilot breaks out of the clouds and establishes visual contact with the runway. With the translation complete, look past the codes and evaluate the operational reality. Professionals focus on how these data points interact to affect flight safety and success. Considered alone, 8 kilometers of visibility suggests a comfortable safety margin for most arrivals. When the temperature and dew point converge within 2 or 3 degrees, as they do here with the 26-24 spread, the air is nearly saturated. This creates an environment primed for the sudden formation of fog or even lower cloud bases. Adding active rainfall to this high humidity creates a high probability of rapidly deteriorating visibility during the final approach. A pilot sees a wet, slick runway and anticipates that 8 kilometers of visibility could drop significantly in a matter of minutes. Effective weather analysis requires using these isolated data points to build a single, cohesive picture of the flight conditions. Compare the initial raw string on the left against the clear visual picture on the right. You have now developed the skill to translate raw code into a mental map of the physical environment. Test your new skill right now. Click the link in the description to look up the live METAR for your local airport and compare the code on your screen to the actual weather outside your window. Every time you decode one of these reports, you are practicing the exact same critical decision-making process utilized on the flight deck every single day.